We are considering another graph now. In this graph, the temperature is taken on x-axis and pressure is taken on y-axis. The graph is a straight line with the angles theta 1 and theta 2. The options here are V1 less than V2, V1 equals to V2, V1 greater than V2 and V1 less than or equal to V2. Now, what actually we do here is, the graph is a straight line, so we try to consider the slopes of the graph. The slope of the graph is given as m equals to tan theta, which is equals to value on y-axis by value on x-axis. So, m equal to tan theta equal to p by t, implies T by P equals to 1 by tan theta. From ideal gas equation, we have PV is equals to nRT, implies V equals to nRT by P, implies V is equals to nR by tan theta. As nR equal to constant, V is inversely proportional to tan theta. Theta 2 is greater than theta 1, therefore V2 is less than V1 or V1 is greater than V2, and V1 is greater than V2 is third option. Now let us consider a model on ideal gas equation. The problem says here, a column of mercury of 10 centimeters length is contained in the middle of a narrow horizontal 1 meter long tube which is closed at both the ends. Both the halves of the tube contain air at pressure 76 centimeters of mercury. By what distance will the column of mercury be displaced if tube is held vertical? Okay, fine. Is it clear? Next. Here first of all we are given a tube which is closed at both ends and mercury column exists exactly in the middle. The length of mercury is given as 10 centimeters and remaining lengths are given as L each. Total length of tube is given as 100 centimeters. From the diagram, L plus 10 plus L equal to 100 implies 2L plus 10 equal to 100, L equals to 45 centimeters. Now the glass tube is made vertical. When the glass tube is made vertical, the mercury gets displaced by a small displacement y, so that length of A increases by y, whereas length of B decreases by y, so that we are having L plus y in A and L minus y in the B part. Okay. Now let us try to compare the horizontal position of A with the horizontal position with the vertical position of A and horizontal position of B with the vertical position of the B. Okay. The ideal gas equation says that PV by NT is equal to constant. According to this, okay, for side A, what we have got is P naught into L into A by NT is equals to PA into L plus Y into A by NT. From this, PA is equals to P naught L by L plus Y. For side B, P naught L into area of cross section A by NT is equals to PB into L minus Y into A by NT. From this, PB is equals to P naught L by L minus Y. In equilibrium state, pressure at A plus pressure of the mercury is equal to pressure of B. So what we have got is PA plus 10 centimeters is equals to PB, or what we can say is PB minus PA equal to 10, implies P naught L by L minus Y minus P naught L by L plus Y is equals to 10. On simplification, we get Y equal to 3 centimeters, which is second option. Now let us try to move transmission of heat. There are various modes of heat transfer from one body to another body. The various modes are, the first one we say here is conduction. Second one we say is regarding convection, and the third one is regarding the radiation. Now let us try to understand regarding the conduction part. It is a mode of transmission of heat. It is a mode of transmission of heat from one point to another point without actual motion of particles. When you arrange a metallic rod end in the fire, the heat transfers from one point to another point without actual motion of the particles. This kind of transmission of heat is nothing but called as conduction. Same manner, let us try to understand about the convection. It is a mode of transmission of heat with actual motion of particles. This kind of heat transmission exists in the case of liquids. Okay? Then radiation. A mode of heat transfer without actual involvement of medium. And radiation is the quickest mode of transmission of heat from one point to another point. Sir, zoom cheskondi sir. Now let us say something about conductivity. The ability of a material to transfer heat through it is called conductivity. We have coefficient of thermal conductivity. Let us consider the following case to understand the coefficient of thermal conductivity. Consider a metallic rod of length L and area of cross section A fixed between two ends, having temperatures theta 1 and theta 2. Let theta 1 is greater than theta 2. Then heat transfer will take place from theta 1 to theta 2 through the metallic rod. The rate of heat flow depends on length of the rod, area of cross section, and difference of temperatures. The rate of heat flow Q by T is directly proportional to area of cross section. It is also proportional to difference of temperatures. It is also proportional to 1 by L. On combining all these three, what we get here is Q by T proportional to A delta theta by L. Bringing the constant, we get Q by T is equals to K into A delta theta by L, where K is given as Q by T by A delta theta by L, and K is called coefficient of thermal conductivity. It is defined as rate of heat flow per unit area per unit temperature gradient. Delta theta by L is called temperature gradient. The above equation can be given as written as delta theta equals to Q by T into L by Ka. This equation is just analogous to V is equals to IR. Here, in the case of V is equal to IR, V represents potential difference, I represents rate of flow of charge, R represents electrical resistance. In the same manner, delta theta represents temperature difference, Q by T represents rate of heat flow, and L by Ka represents thermal resistance. So thermal resistance RTH is given as L by Ka. Now let us try to do a model upon coefficient of thermal conductivity. A problem is given. The temperature of the two ends A and B of a rod of length 25 centimeters and a circular cross section are 100 degrees Celsius and 0 degrees Celsius respectively. In the steady state, the temperature at a point 10 centimeters from the end B is, the options given are 140 degrees Celsius, 60 degrees Celsius, 80 degrees Celsius and 100 degrees Celsius. Okay. In steady state, a word is mentioned in the problem, said as what? Steady state. Okay. In steady state, temperature gradient remains constant. Implies delta theta by L is equals to K. Let theta be the temperature at the end of 10 centimeters from B. So delta theta 1 by L1 equals to delta theta 2 by L2 implies 100 minus theta by 15 centimeters is equals to theta minus 0 by 10 centimeters, from which what we can get is 1000 minus 10 theta is equal to 15 theta implies 25 theta is equals to 1000 and theta is given as 40 degrees Celsius and 40 degrees Celsius is the first option. Let us have another model in the case of thermal conductivity. Two walls of thickness L1 and L2 and thermal conductivities K1 and K2 are in contact. If the temperature at the outer faces are T1 and T2, the temperature at the common wall is, let us imagine the joint of two walls is as shown in the figure. Okay, L1 is the length and L2 is the other length. Okay, and K1 and K2 are the coefficient of thermal conductivities of the two walls. At the first end the temperature is T1 and at the second end the temperature is T2 and theta is the temperature at the point of contact. As the T1 is greater than T2, the heat will flow from the end K1 to the end K2. Okay, in steady state, rate of heat flow remains constant. Implies Q1 by T is equals to Q2 by T, but Q by T is equals to Ka delta theta by L, but Q by T is equals to Ka delta theta by L implies K1 A T1 minus theta by L1 is equals to K2A theta minus T2 by L2. Cancelling A on both sides and opening the brackets, we have K1 T1 by L1 minus K1 theta by L1 is equals to K2 theta by L2 minus K2 T2 by L2. taking theta common, we have got K1 by L1 plus K2 by L2 is equals to K1 T1 by L1 plus K2 T2 by L2. Completing the LCM part, we have got K1 L2 plus K2 L1 is equals to K1 T1 L2 plus K2 T2 L1. L1 L2 gets cancelled on both sides. So we have got theta equals to K1 T1 L2 plus K2 T2 L1 by K1 L2 plus K2 L1. The thermal resistance of the non-uniform cylindrical rod of thermal conductivity K and length L as shown in the figure is up till now we are considering uniform cross section of the rods, but now we are considering a non-uniform cross section of the rod. Okay, fine. It is having radius A at one end and radius B at the other end, and the length of the rod is taken as L. Okay. Now in this case what we do is we consider change in radius per unit length. For this purpose what we do is we consider a small circular portion of width dx at a distance x whose radius is given as r. Accordingly, b minus a change in radius for length L, then r minus a is the change in length for x. Accordingly, what we have got? R minus a into L is equals to b minus a into x, from which what we are having is r minus a is equals to b minus a by L into x. Then r is given as a plus b minus a by L into x. But we have thermal resistance R equals to L by Ka. So that for small portion thermal resistance is dr, which is equals to dx by k into pi r square. Substituting the r value, we have dr equals to dx by k into pi into r square, where r is given as a plus b minus a by L into x whole square. Integrating on both sides, we get thermal resistance R equals to L by K pi AB. Remember this relation for doing the problems in shortcut manner. Whenever you are given radius A and radius B of the ends and length of the non-uniform rod, then you can use this formula directly for finding the R. This formula is useful for you for finding the thermal resistance of non-uniform rods in a direct manner. Now let us try to understand about series and parallel combination of the metallic rods. At first, we will consider about series combination of rods. Consider two metallic rods of length L1 and length L2 which are having same area of cross section are joined together as shown in the figure. Let theta 1 is the temperature at one end and theta 2 is the temperature at other end. K1 is coefficient of thermal conductivity at one end and K2 is coefficient of thermal conductivity at other end. Then in that case, okay, theta is the common temperature at the joint of the two rods. Rate of heat flow remains the same in both the cases. Then in such case, what we can write is rate of heat flow is equals to rate of heat flow Q by T is equals to Ka delta theta by L. Here Q by T is equals to Ka by L can be taken as resistance, so delta theta by R. So delta theta is given as a power into resistance. Delta theta is given as power into resistance. Okay. Now for first rod theta 1 minus theta is equals to power into R1. For second rod theta minus theta 2 equal to power into R2. Adding both the equations, theta 1 minus theta is equals to PR1, theta 2 minus theta 2 is equals to PR2, we get plus theta minus theta gets cancelled off, theta 1 minus theta 2 is equals to P into R1 plus R2, taking P common, okay, fine. Now theta 1 minus theta 2 I can write as power into capital R. So power into R1 plus R2 on right side. Power getting cancelled on both sides, R equal to R1 plus R2. Okay, whenever the resistances, whenever the rods are in series combination, we have their effective thermal resistance as R equal to R1 plus R2. This implies L by Ka is equals to L1 by K1A plus L2 by K2A. This I can write as L1 plus L2 by K equals to L1 by K1 plus L2 by K2. If both the lengths are equal, then we have the formula as two L by K equals to L by K1 plus L by K2. We get 1 by K is equals to K1 plus K2 by 2K2, or simply K equals to 2K1 K2 by K1 plus K2. Now let us try to understand about the parallel combination of metallic rods. Okay, two metallic rods of same length and may have different area of cross sections are fixed between two ends having temperatures theta 1 and theta 2. In the parallel combination of rods, the effective resistance is given as 1 by R equals to 1 by R1 plus 1 by R2, but R equals to L by Ka. On substituting here, we have got Ka by Ka1 by, I'm sorry, retake from here onwards. On substituting, we have 1 by L by Ka is equals to 1 by L by Ka1 plus K1A1 plus 1 by L by K2A2. We have got Ka is equals to K1A1 plus K2A2. If area of cross sections are same, then K equals to K1 plus K2. Now let us try to take a model on coefficient of thermal conductivity. A room has double paned window of area 1.2 meter square with air gap of 0.5 centimeters. Glass has a thickness 2.2 millimeters. Temperature outside the room is 36 degrees Celsius and inside is 26 degrees Celsius. What is the heat flowing into the room for every hour? We are given the coefficient of thermal conductivity of glass as 0.8 and we are given coefficient of thermal conductivity of air as 0.0234. Here there are bit of calculations in a large manner, so we will try to minimize the calculation part, actually fine. So he said it is a double paned window. The meaning of double paned window is there is a window like this, okay. This is outside and this is inside, okay. Here one glass window, here one glass pane and here another glass pane. We have got in between air, actually air is a medium. This kind of window is called as a double paned window. Air between two glass panes, okay. It is nothing but the combination of three rods. It is nothing but the combination of three rods. So the effective resistance is given, effective thermal resistance is given as effective thermal resistance is given as R effective equals to Rg plus R air plus Rg. This I can write as 2Rg plus Ra, 2Rg plus Ra, where R is given as L by Ka. Here area is given as 1.2 meters square. Length of glass is given as 2.2 millimeters, which I can write as 2.2 into 10 to the power of minus 3 meters. Okay, and air gap, length of air is given as 0.5 centimeters is equal to 0.5 into 10 power minus 2 meters, and coefficient of thermal conductivity is given as Kg equal to 0.8 and Ka equal to 0.0234. Now, substituting the values in this place, R effective is equals to 2 into Rg. Rg is given as Lg by Kg into area plus 2 into plus L air by K air into area of cross section. Substituting the values, we have got 2 into 2.2 into 10 to the power of minus 3 divided by Kg is given as 0.8 into area of cross section is given as 1.2 meter square plus 0.5 into 10 power minus 2 divided by 0.0234 into 1.2. On simplifying that R effective, we get it as 182.6 into 10 power minus 3. 10 power minus 3. Okay. What we have got is power equals to delta theta by R actually. So, power equals to delta theta by R we have got implies delta theta is given as the delta theta value is given as 36 and 26. The difference is 10. So, 10 by 182.6 into 10 power minus 3. The Q by T value is given as 55 joules per second. But we want for 1 hour. The heat flowing for 1 hour is heat flowing for 1 hour is Q is equals to power into 3600 seconds, which we get as 55 into 3600, which is equals to 1.98 into 10 to the power of 5 joules. This is the second option we are getting. Now, another model on this one. 3 rods AB, BC and BD. 3 rods AB, BC and BD made up of same material and having same area of cross section have been joined as shown in the figure. The ends AC and D are held at temperatures 20 degrees Celsius, 80 degrees Celsius and 80 degrees Celsius. If each rod is of same length, length of the rods is also same, each rod is of same length, the temperature at B is, okay, fine. Now, this model is the same as Kirchhoff's current law. As we say, total current entering into the junction is equal to total current leaving the junction. Here also what we have got is the rate of heat flow from C to B and rate of heat flow from D to B, and then from there we are having rate of heat flow from B to A. So what we can say is the rate of heat flow Q by T of BC plus the rate of heat flow from BD is equals to rate of heat flow from AB. But rate of heat flow is given as Q by T is equals to Ka delta theta by L. According to this, what we have got is Ka by L, because made up of same material and having same length and same area of cross section. So, we do not change Ka by L, we change only the temperature part, which we say it as 80 by theta for one rod plus, that is for BC part, and then Ka into 80 minus theta by L for BD rod is equals to Ka into what we are having is theta minus 20 by L, from which what we are getting is 80 minus theta plus 80 minus theta is equals to theta minus 20, which is 160 minus 2 theta is equals to theta minus 20. It is equal to 3 theta equals to 180 and theta equal to 60 degree Celsius, which is option 1. Now, let us try to understand regarding the Wien's displacement law. What it says is, the wavelength lambda maximum corresponding to the maximum intensity is inversely proportional to the absolute temperature of that body. Though according to that, what we have got is, let lambda m be the wavelength and T be the absolute temperature. Then from the statement we have got lambda m proportional to 1 by T and lambda m into T is equal to constant. The constant is taken as B and it is given as 2.9 into 10 power minus 3 meter Kelvin. Okay. A graph is plotted by taking wavelength on y-axis and temperature on x-axis. The obtained graph is a rectangular hyperbola. In the similar manner, another graph is plotted by taking wavelength on y-axis and 1 by T temperature on x-axis. The obtained graph is a straight line passing through the origin. The plots of intensities versus wavelength for three black bodies at temperatures T1, T2 and T3 respectively as shown in the figure are given for us. Okay. The temperatures related are T1 greater than T3 greater than T2, T1 less than T3 less than T2, T1 greater than T3 less than T2, T1 less than T3 greater than T2. Which relation is the perfect one for this graph that we have to identify. For this purpose, what we do is from Wien's displacement law, we have got lambda m is inversely proportional to absolute temperature, lambda m proportional to 1 by T. More is the wavelength, less is the temperature. More is the wavelength, less is the temperature. So accordingly, what we have got from the diagram is lambda 2 is greater than lambda 3 and lambda 3 is greater than lambda 1. Exactly in the reverse order we will be having for the temperatures. T1 is greater than T3 and greater than T2, which is your first option. Another model on Wien's displacement law. Solar radiation emitted by sun resembles radiation emitted by a black body at a temperature of 6000 Kelvin. Maximum intensity is emitted at a wavelength of about 4800 angstroms. If the sun was cooled down from 6000 Kelvin to 3000 Kelvin, then peak intensity would occur at a wavelength of what it is actually. Okay, fine. Now, Wien's displacement law states that lambda m is proportional to 1 by t. From this, what we can get is lambda m into t is equal to constant. So, we can write this as lambda 1 by lambda 2 is equals to t2 by t1. Now, here lambda 1 is given as 4800 angstroms and we have to find the lambda 2 value, whereas the initial temperature T1 is given as 6000 and the peak value temperature is given as 3000 Kelvin. By substituting, we can get it as 4800 by lambda 2 is equals to 3000 by 6000. This implies 4800 by lambda 2 is equal to 1 by 2 and lambda 2 is given as 9600 angstroms, which is your option number 2. After completing the Wien's displacement law, let us now try to take up the Stephen's law. What it says is the amount of heat radiated by a black body per second per unit area. What I am saying, the amount of heat radiated by a black body per second per unit area is directly proportional to the fourth power of its absolute temperature. It is directly proportional to the fourth power of its absolute temperature. So, energy radiated per unit area per unit time is directly proportional to fourth power of absolute temperature. So, E proportional to T power 4 and we get E is equals to constant into T power 4 and the K is taken as sigma, which is called as Stephen's constant, which is taken as Stephen's constant, whose value is given as 5.67 into 10 to the power of minus 8 watts per meter square per Kelvin to the power of 4. So, we obtain E equal to sigma T power 4, which is nothing but called as Stephen's equation. For other than the black body, energy radiated per unit area per unit time is given as E equals to sigma E into T to the power of 4, where E is called as emissivity. whose value varies from 0 to 1, and for human skin the E value is given as 0.98. When a black body of temperature Tb is surrounded by another body of temperature Ts and Tb is greater than Ts, then heat is radiated from unit area in unit time from the black body. In such case, the energy radiated per unit area per unit time is directly proportional to the difference of fourth power of temperatures of black body to the surrounding to the fourth power of surrounding temperatures. Then we can obtain E equal to sigma Tb power 4 minus Ts power 4. Other than black body, E is equal to sigma E into Tb power 4 minus Ts power 4.